now we are talking about the multi-megawatt range, what we are talking about in the wind turbine. And not only that, if you try to talk about in the Indian context, so till 2015-16, you used to see most of the European turbines model coming to India, but post 2016, you can see a lot of the wind turbine which is going to be designed for the Indian environment conditions are coming. So this is that's especially why you can see a lot of drive down of the LCOE, what you are seeing here. So one is we are trying to talk about the rotor diameter increases, and as we try to talk about, if you see the enhancement, the rotor cost increases with the diameter cube, and the rotor power grows with the diameter squared. At the same time, the resource. So based on the resource, and if you try to talk about the mostly in the India and the Asia Pacific region, we are trying to see the medium to low wind regime, unlike the high wind what we are trying to talk about in other parts of the world, particularly the European segment. So to take care of this particular one, today we are trying to talk about a lot of low specific power wind turbine coming up to the picture. That's especially why in the same location, what you used to get between 30 to 35% CEF, today we're getting close to 40% CEF. So, and we are trying to see a lot of smarter rotors and also the components that are lighter, and which is going to be beating the square cube law. So today, this is the kind of a thing going on in the wind industry. So just want to be specific on the specific power part of it, why it is going to be so important. So as you're aware, specific power is going to be capacity by the swept area, and on average, the turbine has grown in height and the rotor dia more rightly than their power capacity. So as you see, as you go increase the up height and the rotor dia, normally you would try to see the increase in the power capacity. But what has happened is over a period of time, particularly taking into account the medium and low wind region, so even though there's a the greater increase in the height of the tower and also rotor dia, but the power capacity has not increased. So this has resulted in the capacity being remain the same, but the swept area is going to increase and the specific power is going to reduce. So this has had quite an impact on reduction in the energy cost, because at the end of the day, the energy cost is the primary driven for any kind of revolution. So today we are trying to talk about the optimized power to swept area, which is an important for the lower LCOE, and particularly when you're trying to talk about the low wind speed sites. So as I already pointed out, where the location we used to get say 30 to 32% today, easily you are getting between 35 to 38%. So that's why you can see, compared to the last 5 years itself, you can see a lot of improvement on that particular one. So here the optimization on the connecting cost, and also we are trying to talk about the offshore part of it, where we are trying to see the same kind of an aspect, where we are trying to talk about it's not a capacity, the energy is going to be an important driver. So the connection cost is going to be reduced because the capacity is going to be higher, but the energy is going to be lower. But whereas we are trying to talk about higher energy, so we are going to optimize on the other balance of component cost also. And further, very important aspect is going to be with the low specific power turbine, we are seeing a less variability. This is a significant aspect in the wind industry, where normally a complaint is going to come saying that wind turbine, the wind generation is going to be variable and it's not be predictable. With the low specific power turbines, we can definitely see the variability is getting reduced and the predictability is increased. In fact, our prediction rate has gone up to 95% accuracy on a day hit. So just to give a brief perspective, if you try to talk about compared with an high specific power turbine to the low specific power turbine, so if you try to talk about a turbine of high specific power having a 530 watts per square meter, which is the phenomenon what you could see between 2000 to 2005, and today we are trying to talk about low specific turbine coming to as low as 170 watts per square meter. So even if you try to talk about this comparison between 530 to 294, so on a given site, the high specific power turbine could produce around 32.4% CEF, whereas a low specific power turbine could go up to 48.9%. Please remember, this is purely what we call the denominator effect. And if you try to talk about on the energy, if you talk about energy part of it, the low specific turbine on the same location is going to generate only 83.7% of electricity compared to high specific power turbine. But considering the connectivity and other bunch of power costs, we are going to see a saving of close to 55% is going to be the things. So if you see between these two particular one, the capacity is getting reduced by 55%, whereas the energy is going to be very normal reduction of only 17%. So this is going to be a game changer, what we are trying to talk about in the last 5 years. And also trying to talk about advanced rotors. And we are having the advanced rotors as we talked about large sweep area, higher reach, providing a greater energy capture and also already reduce the cost of wind energy. And today the more important part is going to be as the blades are becoming larger and we need to start about the more flexible blades and an understanding, especially why today we are having a lot of carbon fibers getting reinforced in the blades. And today you can see most of the blades are very lighter, even though the length of the blade is very increased. And very important, significant thing what we are trying to see in the last couple of years is going to be most of the turbines has got the noise reduction technologies. And here, particularly in the onshore, is going to be very, very critical aspect of it. And compared to the noise level, what you used to see a decade back, today it has decreased by more than 60 to 70%. And other promising technologies on the improving the blade pitch control and other controls are coming up. And we are using a lot of AI techniques and also the controlling mechanism so that we are going to have more optimizing on the wind generation. And they're coming down to the other aspect, which is going to be very, very important, see the wind integration part of it. That all the modern turbines today, it can participate in every aspect of the primary control, secondary control, or tertiary control part of it, including the frequency and voltage regulations. So today, the turbines can go for active power regulations, the reactive power regulations, the frequency and voltage regulation part of it, and more importantly, these turbines are designed for low or zero voltage right through and also the high voltage right through. So the modern wind turbines today can mimic the entire performance of the condenser power plants. That's an important aspect of it. But very, very important here is to understand is, yes, the capability is available, but you need to have a right incentive to be paid. Because please remember, today we are going to be paid based on what's the energy production. For doing this kind of activities, the energy production is going to be limited. So we need to be compensated for the loss of generation. So unless that's going to come in, these turbines can participate in the every aspect of the power system requirements. So just to give the active power control part of it, the wind turbine, the generator can regulate the power output to a defined level, either by pitch action or including the controlling action on disconnection from the grid for a brief period. And it's also possible to increase or decrease the power generation within the specified time. That means you can have very clear ramp rate control also. And also, these active power can be regulated based on the frequency signal. When the over frequency, you can reduce the generation. With under frequency, by operating at a bit of a less level, I can participate in the frequency control also. So this is what we are trying to talk about. If rather than containing the entire wind turbine, you can regulate the power at a set point. Say that we can talk about, okay, you can generate only up to 70% of the capacity. Here with the set point, it can easily take the control part of it. Similarly, if you want to create active power reserve, so you can make the wind turbine to operate at a specific level. That will say is going to give around 20 to 25% power to take care of the frequency regulation. And this kind of a control can be given. The wind turbine is capable of operating at a reduced level, and the moment the frequency is going to go down, immediately is going to ramp up to control the frequency. And if it is again in the larger grid is not an issue, in a small grid, in the microgrid aspect of or in the island grid, the ramping rate is going to be a limitation. So the wind turbines are designed to see to any level of ramp rate limitations. So these controls also will be possible and it can be regulated. So these are the few points I thought of sharing with you. If any questions, I can definitely take.
So thank you very much, Dr. K. Balaraman. It's actually participants. I request you that you please drop your questions in the chat box, and we will just forward these questions to Dr. K. Balaraman, and this response will share with you. So I think because of the time constraints, that means we are following this type of things. So thank you very much, sir, for sharing your
thank you.
Useful talk and wonderful presentation. So thank you very much, sir.
Thank you.
So now I request Dr. Nabanita Datta. She's professor, I think. Are you there, madam?
Hi, yes, sir. Good morning,
Yes,
sir.
it's a welcome. So
Thank
we welcome you here there. And Dr. Datta is professor in the Department of Ocean Engineering and Naval Architecture, Indian Institute of Technology, Kharagpur. And her area is the wind turbine design and constructions, and further the tidal energy extraction also. So I request you just to share your presentation. It's over to you, madam.
Uh, Professor Saini, I've started sharing. Please let me know if my screen is visible.
It's there. It's there.
Okay. So good morning, one and all. Thank you for this opportunity, Dr. Saini. And I would be glad to be presenting a little bit about small wind turbine design and fabrication on campus. And we'll look at the challenges and opportunities. I've been working on this since the middle of 2019. The work was halted because of the lockdown. But whatever we have done, I will try to share and talk about what we have learned out of it. So, because
I request that you please make this in the presentation mode.
Oh, okay. Actually, it is in the presentation mode. Okay, what I'll do is I'll reshare my screen.
Or you can continue. Is there? I think that's visible, clearly visible.
Actually, it was in the full screen mode myself. But what I'll do is I'll share my entire screen. I think then it will go into the full screen mode. Is that okay now?
Yeah, yes.
Okay. Yes, okay.
Perfect.
So we'll be talking about the wind energy in India, which Dr. Balaraman has already given us a good introduction to. We'll look at the small wind turbines. We'll see the challenges and opportunities, and then I'll go a little bit on the details about the on-campus wind turbine design and production that's going on. Okay, so the wind energy map of the country looks like this. We find that the Western Ghats are having really good wind speeds, including Gujarat. I'm here in IIT Kharagpur. This region doesn't have that much good wind speeds. Okay, so we know how the fossil fuel consumption is slowly becoming like we have to stop fossil fuel consumption, and we find that the renewable energy, the consumption of renewable energy has grown slowly. So Professor Dr. Balaraman had this thing in his presentation, LCOE. So the LCOE, the reduction of the levelized cost of energy as far as wind energy is concerned, that should be our main target. This is because if we want to competitively sell wind energy as one of the renewable sources of energy, we need to find out whether it is the LCOE is less than that of fossil fuels. But running fossil fuel plants will become uneconomical by 2030. So we have to exit the fossil fuel era. So the global renewable energy consumption has also increased. We see hydropower is a big competitor, and slowly we are seeing that the wind, solar, and other renewables are also coming up. Now we have some of the biggest wind turbine companies. We see that they are making big wind turbines. Even their smallest machines are in the order of megawatts. And we have companies in India also, the wind turbine companies that are there. They are also making big wind turbines. The reason is that reason why small wind turbines are not being made is we are like small wind turbines. Like we don't have players in small wind turbines because maybe it's not very economical. We don't have enough investment in the small wind turbine sector. So we'll see what are the challenges. Okay, so in India we have lots of installed wind power capacity, and definitely we are seeing that the sizes of wind turbines, as they are increasing, we are able to capture the power capture. It's proportional to the swept area. This circle is proportional to the swept area. Now, a small wind turbine will be defined as a machine with a swept area less than 200 meters square and the rated power less than 50 kilowatts. So now the challenges that come here for large wind turbines. Large wind turbines are still growing in our country. They are not so much as Europe, etc. So the challenges are the investment cost for building large wind turbine is very large in terms of money, manpower, time, sophistication. And they are cost effective when we have at least 10 meter per second wind speed. at least. And the demand of power must be large. The maintenance costs are higher because highly skilled manpower is required. We need dedicated instrumentation also, and the size of the supporting structure and the blades are really going to be large, and their maintenance is also a challenge. Okay, now let's see the opportunities in the small wind turbine market in India. We find that most of our population lives in the villages, and the rural demand for electricity is there, but there are many network faults in the grid which causes power outage for several days in the rural areas. Now, these rural areas are very far off from the power generating stations and from the high tension grid, if you look at the grid map of our country. So, which leads to the voltage drop and energy loss in transmission and distribution. So what we thought is, given if like such rural areas are located in places where the wind energy is good, the wind potential is good. For example, in the coastal areas, we will always be getting the sea breeze. We won't get maybe 10 meter per second, but we can get like 6 to 7 meter per second. So setting up large capacity wind turbine requires huge costs and enough like minimum some infrastructure. So why not set up small unsophisticated wind turbines, which will be both sufficient as well as cost effective as compared to large machines. The multinational companies will be building the large wind turbines. But if you look at the rural areas, we don't have big wind turbines, we won't get investment there. The small and what I'm talking about is local consumption. I'm not talking about these wind turbines being providing power to far-flung places. I'm talking about small wind turbines which can power like maybe a typical village of population of 1,000. So so a small wind turbine of size of power rating 50 kilowatt is what we should be targeting to build in large numbers. But instead of making one big wind turbine of a few megawatt rating, why not make smaller wind turbines of a few kilowatt rating? So the installation will be easier. It will require much less land as compared to solar power and hydropower installations. This will initiate the process of rural self-sufficiency in power. So what are the challenges in the country? There is a lack of formal technological manpower in wind energy engineering. There is also a lack of skilled manpower, especially in blade fabrication. Wind turbine blades are made of fiber reinforced plastic, and the casting of such blades in proper accuracy, because blades are the prime movers. The accuracy and in the design and the construction, that is very crucial. There is infeasibility of energy storage and batteries for stand-alone wind turbines. Stand-alone would mean the wind turbines which are not connected to the grid. They generate electricity and they have to be consumed right there. If you put a battery, the total cost of the wind turbine simply doubles. So that is what is increasing the investment cost and making it an infeasible business model. So there's a lack of skilled maintenance manpower, especially for active control. There are a lot of active control devices in wind turbines, especially the big ones, and even the small ones would require some active control, especially the yaw control. Yaw would mean the change in the direction of the nacelle when there is a change in the wind direction. There is also always the danger of inclement weather. The safety of the turbine needs to be assured, both mechanically and electrically. So, what we decided was, on campus, we'll build a small wind turbine. Let's start from scratch. हमें कुछ मालूम नहीं है, लेकिन कहीं ना कहीं से तो शुरू करना होगा. So let's start from scratch. So that's what we thought, that let's understand how to make a wind turbine by understanding its design and then slowly move into production. So this is what the basic parts of a wind turbine look like. So the motivation was to learn to combine interdisciplinary engineering and make the wind turbine from scratch. Learn various processes that are required, enhance our direction of engineering efforts from research into cost-effective design, development, and manufacturing. Then learn about cost analysis and cost optimization. Then learn about market availability of machinery, equipment, hardware, whatever are the things required, etc. So the novelty is the indigenous design and construction of the blades. This is where the Indian wind turbines become expensive. We have to import the blades. Blade imports would mean the total cost is going up. If we have sufficient knowledge and skill to build the blades right here, there can be a drastic reduction in the cost of the wind turbines. So we want to make a structure which will have minimum sophistication. The design will be customizable. for a certain location with a certain wind potential. The fabrication and the installation will be cost effective, and the maintenance will be easy. So we have some design constraints. If we have to show this novelty, we have to have some design constraints. What are they? We have to minimize many things: material cost, labor cost, weight, sophistication, minimum active control, which are it's the electronics, and therefore we optimize the LCOE, the levelized cost of energy. So let's see what we did. So the on-campus wind turbine. This is the typical concept design of the wind turbine, where wind energy, which is captured by the blades, it goes into, it rotates the main shaft. There is a transfer of momentum from the air to the blades. Then the main shaft transfers the torque, the aerodynamic torque, goes into the step-up gearbox, which rotates the induction generator shaft, and there is a generation of alternating current. This is one strong advantage over the solar energy, which generates direct current. And mostly energy is commercially used in the alternating current form. All right, so so this was the site location. If you see this map, this is the IIT Kharagpur campus map, and this is the area where the institute is. This is the hospital area, this is the residential area. So here we have this building. This building that you see, it is the tallest building in the campus. It's 8 stories. You can see this Google map image, and in the circle, in the red circle, you can see this terrace, and this is the terrace whose photograph I took. Now, this is where we had an anemometer placed for 2 years by one professor from another department, and he was very kind enough to give us that data. So the 2-year wind data we analyzed, we got the wind probability distribution, we got the direction also, how often and how strong we get winds from each of the directions. So the wind probability distribution follows the Weibull distribution. From there, we got the average wind speed, and therefore the design wind speed. We came to know of what is our wind potential on campus, and from there, how big a wind turbine we can make and how much we can power we can capture. Okay, this is the energy spectrum. I will not go into these details of this. Okay, so we did the microsighting of the place. Like microsighting would mean what are the obstructions. Wind turbines should not have obstructions at all, because the wind flow into the rotor should not be disturbed. So after that we studied the cut-in and the cut-out wind speed. What should be the minimum and the maximum wind speed at which the wind turbine must operate. Through that, we had a few calculations, and that's how we found out what should be the size of the blade. The size of the blade depends upon the available induction machines that are available in the market, and how big a blade we can make on campus. We found that we can make a blade of maximum like 4 meters or so. The blade is being made in the marine construction laboratory of our department, where we have a lot of FRP fabrication going on, and we have skilled manpower in FRP fabrication for the last 15 years. So that's how we chose the machinery, and therefore we have designed a 250 watt wind turbine. It looks like this. It is horizontal axis, 3-bladed, and the radius is, we can see, 3.38 blade radius, and we'll have a single tower. It will have active yaw control with anemometer, microcontroller, and a slewing bearing. So therefore, the basic design, we found out what the general configuration of the wind turbine is going to look like. So this is like designing it from the scratch from given wind data, from available wind data. So we have the general configuration and the generator. We designed this. The complete project was done by undergraduate students working with me across departments: aerospace, mechanical, civil engineering, electrical engineering, as well as my own department, ocean engineering. And we have also been ably supported by Department of Metallurgy and Materials Engineering, who have helped us in testing the FRP blades. I'll continue. So the induction machine was chosen. The induction machine and the gearbox were together. So we came to know what was the RPM at which the motor must rotate so that it acts like a generator. The blade was designed, the aerofoil section was chosen. So the blade was designed, and the blade aerodynamics was studied. That is the drag and the lift distribution, the thrust and the torque distribution along the length of the blade. So this was studied, and therefore the correct pitch angle, the correct twist angle of the blade was also generated, and we got this blade geometry. This is a 3.24 meter long blade. The lower half provides the structural strength, and the upper half, about the top 60%, provides the main aerodynamic torque. Okay, so this blade is going to be made of FRP. We have tested these FRP samples, several of them, to choose the most optimal one for our strength and vibration conditions, which will withstand our conditions here. So this is a photo from the Metallurgical and Materials Engineering department. So the blade fabrication process will be with the help of chop strand mat, CSM, woven mat, etc. So 5 layers of these FRP mats will be used, and they will be cast together with resin and hardeners. So the tests have been done, samples have been ready, and we'll see how well we have progressed. The static analysis and the dynamic vibration analysis of the blade were also done, and associated conference publications were also made by the students working with me. So the hub was designed. The hub was designed such that it is able to, it holds all the 3 blades together. Then we had, just a moment, yeah. Then the drivetrain. The drivetrain is, if you look at this picture, this is the main nacelle. We designed the blade, we designed the hub. Then after the hub, we have the main shaft running. The main shaft will have brakes so that it can, so that the overspeeding can be stopped. Then we have the gearbox and the induction machine. So this whole drivetrain with the machinery is housed inside the nacelle, and the nacelle sits on the top of the tower, which is able to rotate with changing wind direction. So the main shaft was also designed. The shaft was designed such that it is able to take all the stresses. This design was done by my student from the Department of Mechanical Engineering who worked with me. The bearings and the couplings were also chosen to meet the torque and the RPM characteristics. And the tower was designed such that we are able to get sufficient height for the blade to rotate. The foundation was designed such that the wind loads are neither able to slide it nor able to topple it. So the extreme wind load conditions were taken, like 50 meters per second. That's a huge wind speed which will occur maybe once in 30 years or so. Okay. The foundation was designed keeping in mind these the extreme loads. The supporting structure was completely studied in the STAD Pro software, and then this structure came up. The tower was analyzed also for dynamic loads of the wind, both for gust as well as for the turbulence that comes in. So turbulence and gust both are present, and we find that the structure does not resonate with the gust frequency. I'm so sorry, and neither with the maximum frequency in the turbulence spectrum of the wind loads. So this is how the nacelle will look like. At the top, it will also have an anemometer. So right now, this is a 5 lakhs project funded by IIT Kharagpur itself, internal project, because it's an undergraduate student project, but we have been working hard on it to get it in shape. We have also studied how the slewing bearing will look like, and the anemometer, etc., how the yawing will be done. I'll not look at go into the details of the control systems. We are still working on it, but of course there will be a microcontroller which will look after the yawing as well as the braking of the main shaft. Both are necessary for safety of the wind turbine. Now, at the background, please keep in mind that we are trying to always keep in mind that we are minimizing the cost. We are trying to keep our machinery as simple as possible. The instrumentation, etc., will also come in, but these will be simple. Okay, now let's come to the production. In the production, you can see in orange, this is me on the site, and here we started with the construction. I'll go through these photos quickly. The construction of the pedestals were done. You see, then we had the structure being made. The structure here, right here, the iron structure, it has to be heavy. Then the tower, you can see me doing some welding. Then the tower was installed. Once the tower was installed, the phase 1 of this production was over. So we also had the electrical infrastructure, the cables laid out right there. Okay, so once the tower was installed, we moved into the blade fabrication. So the blade fabrication, we had to first make the mold. You can see the aerofoil stations of the blade. The blade was then, the blade mold was then made. I'll just tell you. Let me move here. Yeah. This is the blade mold that is ready after a lot of shaping of the blade mold with the help of rubber, putty, chalk powder, etc. You can see this is our marine construction lab where people are, the people working here are skilled in FRP fabrication. So, right. So the blade mold was ready. Now the blade mold is like it will be there, it will not be the final blade. Now on this mold we made the die. The die will help us in making the final casting of the blade. So the final die looks like this. The two parts of the blade, the suction side and the pressure side, the two dies are there, and inside them we will make the final casting. And now we are facing a little bit of challenge in how to join the two sides of the blade from inside. But we are in talks with professional tape manufacturers. There's a company called 3M, and they are providing us with industrial adhesive tapes, which will help us in joining the two sides from inside, and we'll have a full blade ready. So this is 3.24 meter long blade. Now, as you can see, the two dies, when they are joined together, and you see inside, you can see the airfoil sections, you can see the twist of the blades, and you are reaching till the end. So the blade die is ready. The inside surface is extremely smooth. It has to be smooth so that we get the best aerodynamics and no energy is lost in vortex generation. So now we built the hub. There was a lot of work again going on. It was all during the lockdown. This was earlier this year. Lockdown, what I would mean is the whole production process started without the support of the BTP or BTP students. I was doing it by myself, but that's not the thing. The work was slowed down because of this lockdown as well as other conditions. Okay, so the hub was ready. The hub was bolted. You can see on the three sides the blade will come. This location is the central workshop of IIT Kharagpur. In the center, you will have the main shaft bolted. So the bolts were also designed. How thick the bolts should be and what material it should be. Those were also designed, and the suitable one was picked up from the market. So the design was done by the students from Mechanical Engineering Department. This was the main machinery. You can see the induction motor, and the blue part is the gearbox. So they came together, and the yellow part is the shaft, which attaches itself to the main shaft. And this is this side from which the aerodynamic torque enters. The energy transfer is towards the left. It goes into the induction motor, and from there we have the mechanical energy being converted into electrical energy. Of course, we have to know the efficiencies, which we know already. Okay, so professors from Electrical Engineering Department came and inspected the machinery, and then it was tested in the Department of Electrical Engineering for its torque and RPM characteristics. Okay, then we moved into the components, the hardware components.
Excuse me. May I request you that you please
okay. Yes, just one more minute. Yes.
Thank you.
So the parts of the blade were made like this. The parts of the hub were made like these. These were connectors, and this is the main bed plate that you see. And this bed plate assembly is now going to begin, because we are now getting the components of the drivetrain. So this is the nacelle. As you can see, the nacelle is getting assembled, and the flange making is now in progress. So I would like to thank all the subject matter experts who have helped me on campus to make this wind turbine. So that's the end of my talk. I'll be happy to answer some questions. Thank you.
Thank you very much, Madam and Datta. And it's really wonderful, and it's a motivated talk, and you have given that, because it is very much required to our students and researchers, so that immediately they should know that how the technology and the research can be brought and can be fabricated and can be put in the field. And of course, it is for a small capacity, which is the need of our in the rural areas where the energy wind potential is less. So there can be. Thank you very much.
Okay, thank you so much, sir.
Thank you. So now before lunch, there's last speakers, Professor Abhishek. He's in the Department of Aerospace Engineering, Indian Institute of Technology, Kanpur. So I request